In this video, we'll talk about section 9.2 and 9.3. In 9.2, there are just some formulas that you'll need to know to do some calculations. The first one is the circumference of a circle. The circumference of a circle is the distance all the way around it, and it can be calculated by pi times diameter. And just as a refresher, radius is from the center of the circle to the endpoint, while the diameter is straight across going through the center. The area of a circle can be calculated by pi r squared. The next one is an arc length. And what the arc length is it's a portion of the circumference. And how you calculate the arc length is that you'll need to know the angle formed from the center by two rays. And you're going to take that angle and put it over 360 and then multiply it by the circumference. So in other words, the angle divided by 360 times pi times the diameter. Now, the angle over 360 is just basically a fraction of the circle, and therefore a fraction of the circumference. The next formula is area of a sector. The area of the sector has to do with kind of a piece of the circle. So in this case, it would be this area. Now, just like you calculate the arc length, you're going to calculate the area of a sector in a similar way, except you're going to take a portion of the area. So again, we are going to take an angle over 360, that gives us the portion, and multiply it by the area. So in other words, the angle over 360 times pi r squared. The last thing we'll talk about in this section is an inscribed angle. And what an inscribed angle is it's an angle that doesn't necessarily go through the center. So in this case, you can see there's an angle that goes out to here. There's an angle that goes here. And then there's also two on the other side, here and here. Now, the thing to know about this is that when you do have an angle, there are kind of two things that can come about this. If this angle right here, let's just say it is 40 degrees, the arc length of it, coming from the rays of the angle, is double. So the arc length of this would be 80. And vice versa, and you'll notice how those angles overlap with the other side. If the arc length is 80, the angle will be half, which will be 40 degrees. In section 9.3, it has to do with the altitude to the hypotenuse. So if I have a right angled triangle, and from the right angle, I create an altitude to the hypotenuse, meaning I create 90-degree angles. You should notice a few things that happen. Let's label this A, this B, this C, and this D. The first thing that you should notice is that there are three different triangles. There's the bigger one, and then the two smaller ones that we created when we drew the altitude. Let's take a look at this triangle right here compared to the larger triangle. So we have triangle ABC and we have triangle ADB. What you'll notice in both triangles, they have 90-degree angles. So that means that one of the angles is congruent. But what you should also notice is that they share an angle, A. Therefore, triangle ABC is similar to triangle ADB. Now let's look at this other smaller triangle, again to the perspective of the larger one. So triangle ABC and triangle BDC. Now again, you'll notice that they both have 90-degree angles, which gives us one angle congruence. Again, you should notice that they share angle C right in here, which will give you angle similar. Meaning, again, these two are going to be similar. And then based on the transitive property, we can basically then say that all three triangles will be similar to themselves because they're all considered similar to that bigger triangle. We'll be using this in a few examples to prove to find lengths of sides based on their proportions. Now, here are some conclusions that we drawn. We already stated the first one, that the two triangles formed are similar to the given right triangles to each other. And we already stated that. The second is the altitude to the hypotenuse is the mean proportion between the segments of the hypotenuse. So x over the hypotenuse equals the hypotenuse over y. And then finally, either leg of the given right triangle is the mean proportional between the hypotenuse of the given right triangle and the segment of the hypotenuse adjacent to that leg. And you can see that as a setup right here. For example, we're going to use one diagram, but we're going to kind of change the size of them and to find the lengths of the missing segment. So what we're going to do, and which will be helpful, is that we're going to label our diagram for A. We're going to say that NM is 9. We're going to say that NO is 25. And then we're going to say that PN is X. Now, usually what's best to do is to kind of highlight the triangles that has two of the sides. So we see that triangle down there. We see this triangle right here. And usually what I kind of like to look at it as is there are three parts of the triangle. There's a short side, a long side, and then the hypotenuse. And then they're all proportional based on that. Or else you can use what was given in that Theorem 68. So if you notice, in the blue triangle, 9 is the short side, X is the long side, and in the yellow, X is the short side, and 25 is the long side. So there's a relationship between the short and the long, and I'll use that setting up the proportion. 9 over X equals X over 25. Again, in the blue triangle, the 9 is the short, the X is the long, but in the yellow triangle, the X is the short, and the 25 is the long. You'll do some cross multiplication. X squared equals 225. And if you take the square root, it's plus or minus 15. But since the length can't be negative, we have 15. Now let's fill in for letter B. If I give that OP is 7, square root of 2, and ON is 7, and we want to find MO, which is this right here. Again, let's look at what the triangles are that are given. We're given this piece down here, and then we're given this one right here. Of the yellow triangle, 7 is considered the long piece. 7 square root of 2 is the hypotenuse. And from the blue piece, 7 square root of 2 now is the long piece, and x is the hypotenuse. So again, we're using the relationship of hypotenuse to the longer side, or vice versa, long to hypotenuse, and you'll set that up. So you'll get 7 square root of 2 over 7 equals x over 7 square root of 2. Again, you'll do some cross multiplication. You'll get 49 times 2 equals 7x. X equals 14. So MO has a length of 14. Letter C gives us that MN is 4, NO is 8, and we need to find MP. Again, highlighting our sides that we need, or that we have, you'll see that those are the two triangles. Based on what we have short over the hypotenuse. So I'm going to set it up as that, short over the hypotenuse. From the yellow section, I have 4 over x equals x over 12, because I need to add the 4 and the 8 together. X squared equals 48. X equals square root of 48. I will rationalize, or reduce, so that will be 4 square root of 3. And finally D. If we have Pn equals 12, On equals 20, and we want to find PM, what we'll do in this case is that you notice, based on the sections given, in the yellow we're given the short and the long side, but in the purple we're given the hypotenuse and the long side. But if we have two sides out of a triangle, we can find the third missing side based on special triangles, or Pythagorean theorem. So we'll do 12 squared plus 20 squared equals PO squared. 144 plus 400 PO squared. 544 equals PO squared. Square root of 544 equals PO, which simplifies to 4 square root of 34. So setting up the proportion, we'll do long over hypotenuse. So we'll do 12 over x over 20 over 4 square root of 34. 20x equals 48 square root of 34. Divide by 20. X equals 12 over 5 square root of 34.